Hello all and welcome back to this course on computer organization. So having looked at almost all the important instructions, the move, data transfer, ALU instructions, the branching instructions, jump on no zero, jump on zero, and finally the stack operations, the one class of instructions that remains to be seen is that of function calls. Okay, so let's look at that. Function calls. So it's very common for us to use the idea of functions in a C program, right? The moment you want to write something in a modular fashion, you write something as a function and then just call that function, okay, again and again, so that the code is localized and stuff like that. Now, writing a function and in C that can be translated to something equivalent in assembly is quite involved, okay, and therefore we need to understand what this idea of a function call or a subroutine call is in a assembly language sense, okay. So let us assume that I have some function which will do something very simple like adding two numbers, okay. It will add, let's say I have a function that can add EAX and EBX. Okay, all I want this function to do is implement this addition of EAX and EBX. Okay, so this instruction itself is not very complex. It is just this, right? Now, you might ask why we would want to write a function for this, because it's just one instruction. But let's assume that, for illustration purpose, this is a very simple example. So, maybe I could do one more thing. It would add this, okay. I want this function to do the following. EAX should get EAX plus EBX minus ECX. Okay. So this is what I want. So now what do I want here? I want to subtract EAX comma ECX. Okay, this is a very simple function that I want to do, and this, these two instructions are going to reside in memory somewhere. Okay, so I will call this function address. This is the function address. It's a label corresponding to some address in memory when the program gets loaded into the memory, okay. So we'll not worry about that at this point. But now I want to write something in assembly language that can call this function, do something with it, and then I need to return. Okay, so let us see what that thing is. So let us say, for example, I am going to write a program now which is in some other unrelated part of the code segment, okay, where I will initialize my registers, move EAX comma 0x 59, move EBX comma 0x 22, and move ECX 0x 35, okay. So after this, what I want is, I want to perform this set of operations, okay. Normally what I would have done is to simply have a copy of these instructions made so that I would just go ahead and execute them in line. I would have just done this, right? It's not very hard because these are only two instructions. But imagine now, instead of these two instructions, I had a bunch of instructions, okay. Or tomorrow I want to change, let's say that I made a copy of these two instructions here, and then I did something else. I made another copy of these two instructions and went on and on, making hundreds such copies. Now tomorrow, let's say I want to change this function. Instead of EAX plus EBX minus ECX, I want to do this. I want to add all three numbers instead of adding and then subtracting one. Then all I have to do is, if I had made it a function call, right? If I had made it a separate subroutine sitting in one location, all I had to do was replace this with add. In one place I go and change that add, and all the other instances where I have called this function would have automatically reflected this new change. But instead of that, if I had made 100 copies of this two instructions, I would have to go to each of those 100 locations and change the subtract to add. Okay, so that's why function calls are very important, and it's not a good idea to just copy and paste code, even though it's effectively going to appear like it's exactly that, right? So for now, for example, I will go back to my original thing where it was, subtracting. So now what I want is, having executed this program up to this point, I need a way for me to switch to this function where this function description exists, execute something, and then return here. Okay, that is the key point that I want. So how am I going to actually switch to this function? So that happens by a very natural mnemonic. What do I do to a function? I call the function, right? And therefore the mnemonic that is used is also call, and I have to give it an address. So I will give it this label. Sitting here, right? So it's nicely called, I'm able to call this, right? And then let us say I'm going to now move EAX, okay, comma, I will say another 0x69, move EBX 0x32, move ECX 0x41. Okay, so I am going to now do this, and then I am going to call this function again. So the execution method by which the execution flow of this program should be like this, right? You continue executing like this in one straight line. Of course, the call has to go there, do something, and then come back here. After you finish the call, you got to come back to this location. Do that, then go again, you do a call, then you come back. So the idea is therefore to go and come back. Now, what is the most rudimentary way of implementing this call? Okay, the call is very easy, right? I just need to transfer control to another location called FUNC-ADDR. So ideally, the most rudimentary implementation of this call would have been unconditional jump, right? Now, suppose I did this, suppose the call were implemented like this, then this program would execute like this, and then it would say, oh, call FUNC-ADDR, and which is basically a jump, and it would simply jump to this location, and it would go ahead and execute this program. No problem, absolutely no issue. The only problem is, after it does the addition and subtraction, where does it go? Of course, after subtraction, there will be some garbage instruction here, right? So after subtraction, the program will continue to execute like this. Whatever in memory, in the code segment, whatever resides there will be interpreted as some instruction, and the program will continue to execute. And therefore, you will get complete garbage in this process. Okay. So what we want to do is, to be able to manipulate this so that you not only go there, but you need to be able to come back appropriately. Okay. So therefore, just a blind jump, unconditional jump is not going to solve this problem for us. Okay. I need to know where to return and where to come back and start execution after I finish the function. Okay. So for example, when you are at this point, when the instruction pointer is here, right, the call instruction, you do call of something, the instruction pointer will auto increment to this location. Let's say this is sitting 4 bytes away, assuming every instruction is 4 bytes, right? Then the instruction pointer already is pointing to the next instruction, which is this move, right? So therefore, in some sense, where to return is already in the instruction pointer when this instruction is being executed. And therefore, in order to execute this jump with the context of being able to return, what you need to do is to store this return address somewhere. Okay, so now let's assign some labels or some addresses here. 0xC100. Okay, I'm going to give it, just 16-bit addresses, not 32-bit. Okay, because there's just a lot of trailing zeros which I'm going to leave out. C104, 0xC108, 0xC1 0C, right? A, B, 8, 9, 10, 11, 12, yeah, A, B and C, right? 0xC1 D, E, F 0. So this will be 10, C110. This is where it is. Okay. So when I am executing the call funcAddr, okay, which is basically going to point to some other address. Let's call this address now as, when it is loaded into memory, C200, and this is 0xC204. Okay, we'll see what that read instruction should be. Okay, so now what I can do is, technically, if I can store this address of C10, so when call funcAddr is being executed, EIP has already been incremented to point to 0xC110. Okay, here in this instruction, EIP instruction pointer is already 0xC110. Okay, now all I have to do is to store this value somewhere so that I can use it for returning appropriately. Now, where can I store this? Technically, I could put this in some register, right? I could put this in the register. But you think about the scenario where we actually make one function call, and from that function I make another function call, I make one more, so I can make infinite function calls actually, right, in a C program, right? So therefore, I will not have enough registers to store this return value for each of these functions, okay? And that is why the memory itself is used to store this return value. So what you do is, when you call a function, the call needs to do two things. One is push EIP onto the stack. It's a memory, right? You push EIP onto the stack, okay? And then I will do an unconditional jump to where? To the function address, right? So this function address also, now we know it will actually be called 0xC200. Okay. So when this function executes, EIP, right? What does the unconditional jump do? It simply loads EIP with this C200. But before that, it has pushed the return address, that is, this 0xC110 will be pushed onto the stack, and then you will, switch the execution to 0xC200. Okay. So these are the two things that are going to implicitly happen when I call a function. So we will look at this, the picture of the stack and many other things later, so that we get a very clear picture as well. Now assume that I have done this, okay. So let us say we have, maybe I'll make a copy of this. Right. So let us say that this is happening and my stack segment is sitting here. Right. So when I execute this particular instruction, right, the EIP of 0xC110 is going to get pushed onto stack. So let's say ESP was pointing here. You will now point here and then you will get 0xC110 on the top of stack. This is my stack segment. Then EIP is loaded with 0xC200, right? You come there, you do an addition, you do subtraction, or you do whatever function description you want, and now I need to return to this point where I had to continue after the function call. What is that return address? It is 0xC100. Where is that? That's sitting on top of the stack. So therefore, I will execute what is known as a RET here. What is RET? It will simply pop the top of stack into the instruction pointer. Okay. Who pushed that for you? The call instruction has pushed that on top of stack, and therefore these two are, there is a protocol that call will push, return will take it, and then it will know where to return. Okay. That's why it is called return, because you are returning to the point where you are supposed to continue execution after the function call. So you execute this particular program in this order. You come here, then you jump to this, then you execute this, you hit return, the top of stack, right? So this is what happens. Let me color code this, right? So when you color code, when you do a call, the stack pointer decrements like this, okay, and this I will write in magenta, right? So when you return, the top of stack is now popped onto the EIP, and you continue from there onto this point. So you know where to continue. Go ahead, execute the next piece of code. Again you are back down like this, right? Again you go a call, you do a return and all that stuff, and then you can continue any number of times like this. So you will see later when we look at how a C program is taken to assembly, you will see that you can make any number of function calls, and this very simple idea works wonderfully well. You will know from every function, you know where to go, do something, and where to come back. Okay, so that is how the call and ret instructions are used in order to handle function calls in a C program as well. So this is how the call and ret instructions are used to handle function calls or subroutine calls in assembly.